How's everybody doing? This is a video for Monday's lesson. I wanted to put together an opportunity for people who maybe didn't have access to the slides, or people who might just want a more visual way of learning the content. That sometimes is helpful. So hopefully you guys have the slides in front of you. The slides that we're going to look at are slides 31 to slides 41. And so I want to be able to go through and just explain to you guys just some of the content, so that we can look at how kind of tying our understanding of types of chemical reactions to predicting products. So last week, what we did is hopefully you were able to determine the different types of chemical reactions. There were 5 different types: combination, decomposition, single replacement, double replacement, and then combustion. And so it's important for us to make sure that we understand those different ones. Remember that combination can also be known as synthesis. And so I'll actually be calling it synthesis from now on. So for chemistry, what scientists found is that it was actually really helpful being able to look at the different slides. And so if you guys want to go to the next slide, slide 32. But the question becomes, right, in the problem so far, we have been given the left-hand side and the product side, or the right-hand side of our chemical equation. And the question becomes, but what happens if you don't have the right-hand side? Right? Scientists want to be able to not do reactions with things that they know. They want to be able to figure out what will happen if we mix things that we don't know. And so chemists don't know the product side. And so the question is, could we potentially find it? Well, luckily, it'll test your abilities, because in order to be successful, we'll have to look at how knowing the 5 different types will help us be able to determine and recognize the reactions. By recognizing them, it'll tell us how to put them together for the products. And so the first one that I want to look at, if you guys want to go to the next slide, on slide 33, is a combination and synthesis. And so a combination or synthesis reaction, it happens anytime that you have a molecule by itself added to another molecule by itself. You have to excuse the hammering if you could hear that. Apparently they're doing construction someplace. But I have a molecule by itself plus another molecule by itself. And what that's going to do is that's going to lead to it being a synthesis. And all you have to do in order for us to solve the problem is put the 2 atoms together. When you put them together, there are some common mistakes. The biggest common mistake is that people forget to charge balance them. Remember that you have to put the charges on the top and then switch them. The charges on the top is how you can determine how many of each one you have. And so make sure that you do that switch, right? Put them together and then flip that switch. Don't forget to charge balance. Watch out for the polyatomic ions. The polyatomic ions, remember, are counted as one element, and so keep that in mind. If you want to go to the next slide, and we'll look at some examples. So for synthesis reactions, 2 or more reactants come together to form one compound. So let's look at the first example. I have calcium plus oxygen, and we want to be able to know what the product is. And so underneath, as you can see, I have calcium all by itself. Remember, if something is by itself, it only has one, except what? I have to do my check. The reason why oxygen is 2 is because what have no fear of ice cold beer, right? And oxygen happens to be one of the diatomics, and so it comes as 2. They come together, and when they come together, you put the charges on the top. I have +2 for my calcium, -2 for my oxygen, and so you could get 2 and 2 on the bottom, which is the reason why I scratched it out. But 2 and 2, which reduces to 1 and 1. One thing you want to remember is that you have to balance the chemical equations, and so that's why I put a 2 in front of the Ca and O, the calcium oxide, because of the fact that we had 2 oxygens on the left and 2 on the right. By putting a 2 in front of the Ca calcium oxide, I have 2 Cas now, so I have to put 2 on the other side. The second example is copper plus sulfur. I have Cu, there's only one of them, and there's only one of the sulfur because, once again, have no fear of ice cold beer, it's not one of them. Then you just put them together because they're both +2 and -2. That means you only have 1 and 1. On the next slide, we're going to look at decomposition. So decomposition is the opposite of a synthesis reaction. And you know that you have a decomposition if you're only given one thing on the reactant side or on the left. Basically, what you want to do is separate the A and the B because they split apart. Like it says on the slide, some common mistakes that students make is that you have to remember the amounts. If it's diatomic, when you split them apart, do that have no fear of ice cold beer check. If it's one of those, it'll be 2. If it's anything else, it'll just be 1. One of the things is be able to spot your polyatomic ions because you're going to want to keep your polyatomic ions together. And so I'm going to look at that polyatomic ion sheet, which should be attached as well in the resources. What are some examples on the next slide? Is here I have barium carbonate. And so barium carbonate is barium with the +2 and carbonate with the CO -2. And what I'm going to do is just literally split it in half. Ba plus CO3. You'll notice that when I separated them, I know that there's only going to be one because have no fear of ice cold beer. It's not one of those. And I kept the CO3 together because it's polyatomic. Underneath that, I have iron 2 hydroxide. And so iron has a +2 charge. Hydroxide has a -1. So I do that charge balance. And that's how I know I need 1 iron and 2 hydroxides. They're going to split apart. So you split them right down the middle. And there's going to be Fe plus OH. How come there's not 2 OHs? Because once again, it's not have no fear of ice cold beer, so it's only going to be 1. I have to balance it by putting a 2 in front of the OH, and then I'm done. The aluminum oxide, we have aluminum oxide. I have to do that charge balance. Remember to do that charge balance at the beginning if they don't give you the left-hand side. +3 for the aluminum, -2 for the oxygen, and then you just split them apart. Al plus O2. I didn't balance this one, but if you were to balance it, what would you get? Hopefully, what you would get is a 2 in front of the Al2O3, a 4 in front of the aluminum, since putting a 2 in front of the Al2O3 will give me 4 aluminum, so I have to put a 4 in front of the aluminum on the right hand side, and then put a 2 in front of, which means a 3 in front of the O2. The next slide, we're looking at single replacements. Single replacements are interesting because how you recognize them, first of all, is anytime you have something by itself and then a partner. And what's going to happen is the A and the B are going to switch. Common mistakes that students make is that they switched the wrong ions. You have to make sure that the A and the B that switch are both the positive ions only. Sometimes students will put the two positives together and then they'll get confused. Also, when you put two things together, anytime you put two things together, you have to put or do the charge balance. What students will do is they'll put the amount that's on the left and just put that amount on the right hand side. You have to charge balance them in order for them to be correct. Make sure that you can spot your polyatomic ions. And then before you can even do the equation, you have to check something called your metal activities. And that'll make more sense once I go over the examples, because your metal activity is important. So let's look at the examples now. So if you want to go to the next slide. So we want to first do a prediction. For the first example, I have Fe plus CuCl2, or copper chloride. As you can see, the iron is alone and the CuCl2 has a partner. Now, before I switch them, what you have to do is check something called the reactivity series. If you look on the right-hand side, in order for the one that's by itself to steal, it has to have a higher priority. And so if you look at the reactivity series, there's a ranking. And the best way I can example, or the best way I can think about it, is it seems like a silly example, but if you see someone, you'd only trade your partner for the other person if they were more attractive. And so you have to make sure that the one that's alone has a higher reactivity, because the chlorine isn't going to want to leave what it has for something that's worse. And so, as you can see, the Fe, the iron, is higher than the copper, and so it will switch. And so when it switches, the copper is all by itself now, plus the Fe, which has a +3 charge, and the chlorine has a -1. Then I have to make sure that I don't just take the amounts from the left, because a common mistake the students will make is they'll put Cl2, because we had Cl2 on the left, they'll put it on the right. You have to make sure that you charge balance it, because if you don't, you'll get it incorrect and your balancing will be incorrect. So that's how I got Fe1 Cl3, is because of that charge balance. Then you would look and balance it, and when you balance it, I put a 2, a 3, 3, and then a 2, looking at how to balance the different chemical equations. For example number 2, I have Pb plus gold nitrate. And here, once again, before I even switch them, I'm going to look at my metal activity to make sure that the lead is higher than the gold. And if you look, lead is higher than gold, and so it is going to make the switch. However, the gold is by itself. On the right-hand side, I have to do what? I have to do my charge balance. My lead has a +4. My NO3 has a -1, and then they switch their charges, and so that's how I know I have 1 lead and 4 NO3s. Then I balance the chemical equation in order to make sure that I have the same on the left as I do on the right. For the third example is a good example because it's an example that doesn't work. This is an example of one that I like because it's an example of one that doesn't work. I messed this up. It's supposed to be copper, But let's say that I have copper trying to steal from the sodium. If you can look on the reactivity series, you'll notice that the copper is below the sodium. And so because the sodium has a higher reactivity, then the copper won't allow it to steal. And so it doesn't work. And so keep that in mind. You have to look at your reactivity series before you see it. And so make sure that you look at that. The next slide is one that has double replacements. Double replacements, luckily, are usually the easiest ones to spot. It's one that has a partner plus one that has a partner, and then they do the switch. They switch the positives. Make sure that you switch the positive ions. Like I said, some people will put the positives together and then the negatives together, and then they'll get confused. When you switch them, you have to do the charge balance and not just write what's on the left on the right-hand side. Make sure that you can spot the polyatomic ions, and you should be okay. Like I said, usually this one is a lot easier than the other ones. Oh, my GIF doesn't work. Sorry. Let's look at some examples on the next slide. So for the first example, I have calcium hydroxide plus hydrogen phosphate. And so as you can see, the calcium and the hydrogen are going to switch. And so now there's an H with an OH and a calcium with the PO4. Now you have to do your charge balance, and that's the reason why I don't have 3 H's on the right. I only have 1, and I don't have 2 OH's on the right. I only have 1, because when you do the charge balance, both of those have a +1 charge and a -1. Meanwhile, the calcium, I need 3 on the left, on the right, and 2 PO4s on the right-hand side. And that's because of that charge balance. +2 for the calcium, -3 for the PO4. And when they switch, you have to charge balance it. That gives you the ability to balance it. And so, use your balancing skills in order to balance it afterwards. Once again, I do want to caution, don't just put what's on the left on the right-hand side. It's a common mistake the students make, so you want to make sure that you don't do that. For the second example, I have, once again, a partner plus a partner. There's the potassium carbonate plus the barium chloride. And so the potassium and the barium are the positive charges, and so those will switch. I have a barium and a carbonate on the right-hand side. Both of them are +2 and -2, so you only need 1 of each. Same thing with the potassium, because the potassium is +1 and the chlorine is -1, and so they only need 1. In order to balance it, I put a 2 in front of the KCl, and that should be good. But you have to make sure, once again, that you switch the partners and then charge balance it. The last one, or last part that I'll go over, is the combustion one. And the combustion one can sometimes confuse some students. Anytime you see some amount of CH plus O2, and it doesn't matter how much CH you have. It could be C1000, H2000, plus O2, and no matter what happens, it'll always have the same exact products. It's always just CO2 and H2O. It's always that same thing. CO2 and H2O. CO2 and H2O. No matter how much or how many you have, it's always that. There aren't any examples for this, and I will say that balancing these particular types of reactions can be a little tricky. because of the fact that you always have to go through the same order. You have to balance the H's, then balance the carbons, then balance the oxygens at the end. And the important thing is to remember that the number in front of the H2O that you put has to be even. So, for instance, if you were to put an odd number like a 3 in front of the H2O, you have to double all the numbers and make it a 6 instead. And that's pretty much it. This, to me, is the easiest one to spot if you're paying attention. That's pretty much the lesson for this particular portion. Being able to do this, though, is both the hardest part of the reaction parts or units, and to me also kind of the most rewarding part, because it's actually really useful, especially in real life. These are pretty much the notes. I hope that you guys found that this is useful. Please look at the answer key, and hopefully that'll help guide you. Feel free to ask any questions, and feel free to message me, or you can save them for our Friday meeting. Just a programming note, I think on Friday, some people wanted to meet in the morning, some people wanted to meet in the afternoon. So I think what we're going to do is we're going to have 2 separate meeting times. One of them is going to be at 11:30. The other one is going to be at 2 o'clock. Anyway, if you haven't sent in your responses, please do that, because I want to be able to make sure I support you guys in all the ways that I can. Anyway, I hope that you guys are doing really well. I miss you. All that stuff. Keep staying positive. I promise you we'll get through it, and everything will be all right. All right. Later days.